In this video, we'll look at arc length. Let's assume we have this function f of x, and we want to measure the length of that curve from A to B. Imagine if that curve were a string, and we stretched that string out. We're looking for the length of the string between those 2 points. The formula to do that is given here. The integral from a to b of the square root of 1 plus f prime squared dx. Or we could also use the Leibniz notation. The first thing we need is y prime, the derivative. We'll get x to the 1/2. Now the length of that arc is the integral from 0 to 2, using the bounds that we were given, of the square root of 1 plus the derivative x to the 1/2 squared dx. We can rewrite this as the integral from 0 to 2, square root of 1 plus x dx. Let's do a u substitution. We'll let u be 1 plus x. Then du is simply 1 dx. Now our integral looks like the square root of u, du. Our new limits of integration, if we plug the lower bound 0 in for x, we get 1. And if we plug in the upper bound for x, we get 1 plus 2. The upper limit is now 3. We have the integral from 1 to 3 of u to the 1/2 du. Integrating this, we get 2/3 u to the 3/2. And we are integrating from 1 to 3. This gives us 2/3. Plug in our upper limit, 3 to the 3/2, minus plug in the lower limit, 1 to the 3/2. We now have 2/3 times 3 cubed is 27, then that's the square root of 27, minus 1. We can simplify the square root of 27. That is 9 times 3. That will make that 3 square root 3. And then minus 1. Distributing the 2/3, we get 2 root 3 minus 2/3. This is the length of that arc from 0 to 2. Here we have another definition of arc length, and there's very minor changes this time. Instead of y equals f of x, now we have x as a function of y. So x equals gy. Instead of integrating from a to b, we're looking at c to d now on the y-axis. So again, we're measuring the length of this arc from C to D. Like last time, the first thing we need is the derivative. So let's find, in this case, x prime. The derivative of e to the y is e to the y, and the derivative of 1/4 e to the negative y is negative 1/4 e to the negative y. Now our formula, the arc length is the integral from 0 to 1 using our given bounds of the square root of 1 plus the derivative that we just found squared dy. We'll simplify a little bit under the radical. We have 1 plus, now we'll square that binomial. E to the y squared is e to the 2y. Then double the product of these two. That will give us negative 1/2. and then we square the last term, that will give us plus 1/16 e to the negative 2y. And dy is still there. A little more work under the radical. We can combine like terms. We'll get e to the 2y plus 1/2 plus 1/16 e to the negative 2y dy. It may not be super obvious at first glance, but that is actually a perfect square trinomial. We can write that as a quantity squared. If we take the square root of the first term, we get e to the y. And if we take the square root of the last term, we get plus 1/4 e to the negative y. Notice if you square this binomial, you'll get this trinomial that we have here under the radical. Square the first, we get e to the 2y, double the product, multiply these two terms together, and then double it, and we get 1/2. And then square the last term, we get 1/16 e to the negative 2y. We like having a perfect square under the radical because now the radical will go away. We're left with the integral from 0 to 1 of e to the y plus 1/4 e to the negative y dy. If we don't end up with a perfect square under the radical, we may need other techniques like using approximations like the trapezoid rule. At this point, we can integrate. The integral of e to the y is e to the y, and we get minus 1/4 e to the negative y for the second term, and we are evaluating all of that from 0 to 1. Now plugging in the upper limit, we get e minus 1/4 e to the negative 1 minus, we'll plug in the lower limit, that is e to the 0 minus 1/4 e to the negative 0. This gives us e minus 1 divided by 4e, then e to the 0 is 1, so that's 1 minus 1/4, which is 3/4. Then distribute the negative, we'll get negative 3/4. We now have the arc length.